presentation on scanning electron microscopy. Today we will be going through several things. The first thing that we would be going through would be the working principles of how scanning electron microscopy works, followed by an introduction and walkthrough on the equipment that we had the chance to use. Then, we would run through the images that we have obtained and briefly discuss about it before ending with a conclusion. Let us begin by going through what an SEM is. To start off, an SEM is typically an imaging equipment that uses focused beam of electrons and X-rays to probe the surface of a sample, under high vacuum, to produce a high-resolution and magnified image of the sample's surface. It is similar to how a microscope would be used, but in an SEM, electrons are used to view the surface instead of using light. In general, this is how the inside of an SEM would look like. The electrons are typically generated through thermionic heating of a tungsten filament lamp, and the electrons that are generated is accelerated down the chamber by anodes and magnetic lenses that are placed below the electron gun. The electrons are then focused through an aperture using condenser lenses, and are directed onto the sample in a scanning fashion that are controlled either by moving the sample stage, or through the scanning coils. Before the sample could be scanned, the chamber would need to be at high vacuum so that the directed electrons would not be scattered by particles that are present in air. As the electrons are focused and directed onto the sample's surface, the electrons would interact with the sample in either an elastic or inelastic manner, which produces backscatter electrons and secondary electrons that are higher and lower in energy respectively. Primary electrons come from the electron gun situated at the top of the microscope, while secondary electrons originate from the specimen as a result of displacement by the primary electrons. Backscattered electrons consist of high-energy electrons originating in the primary electron beam that are reflected or backscattered out of the specimen. The electrons that are scattered by the focused beam, either elastic or inelastic, would then be attracted to and can be detected by the positively charged detector to give signals that would create the image of the sample's surface. Aside from the SEM machine itself, there is also the control panel and joystick used to control the SEM. The more important feature that is mainly used would be the control panel, where you can fine-tune the focus of the SEM on the sample. On the control panel, it contains the freeze button as well. It allows you to freeze the image and save for viewing later. To start off the practical, the sample that we had was already prepared beforehand. Gold nanoparticles and nickel nanoparticles were chemically deposited onto a thin layer of silicon dioxide plate as shown. However, it is worth to note that if a non-conductive sample needs to be scanned, a thin layer of conducting material needs to be deposited to boost the secondary electron emission of the sample for scanning. Next, we would bring you through how the machine was operated. The SEM was first charged up to the intended voltage used to accelerate the electrons, followed by applying vacuum down to a pressure at about 9.65 times 10 to the power of -5 Pascal, upon loading of the sample into the chamber, as you can see from the image, to prevent the scattering of electrons due to contaminant particles present in air, which would result in poor scanning resolution of the sample. After applying high vacuum, we could fine-tune the magnification of sample using the control panel mentioned earlier. But before we zoom in, it is advisable to locate the area containing the correct sample to be scanned using the low magnification, since it focuses on a larger area. Once selected, you can now see the operator slowly zooming in to focus on the nickel nanoparticles coated onto the sample plate. By using the various knobs that finally adjust the position of the sample stage on the X, Y, and Z axis, the operator can fine-tune the resolution of the image before the image is saved. We then moved on to the second sample, which was the gold nanoparticles that are deposited onto another sample plate. Same procedures were then carried out to capture the image of the coated gold nanoparticles. Before we discuss on the image that was taken for both nickel and gold nanoparticles, there are a few legends in an SEM that are useful to note. An SEM image would usually contain the type of image taken. In this case, it is a secondary electron image. It also indicates the voltage used to accelerate the electrons down the chamber. It is expected that with a higher voltage, penetration of the electrons into the sample would be deeper, which results in a better point-to-point resolution. The image would also contain the magnification and also the working distance of the surface to the final lens of the probe. Lastly, it would also contain a scale that is relative to the magnification, which is useful for size determination. So here we have two images, one of the gold nanoparticles and the other being the nickel nanoparticles. Relative to the scale, they have the respective diameter and length as seen in the image here. Looking at the nickel nanoparticle image, you could see regions of varying colors. From the image, these light triangular portions are the deposited nickel stacked into layers and the dark regions are the silicon plate backing. While both of them are deposited nanoparticles, it is clear that both kinds would have deposited or assembled in different ways, depending on the methods that was used to deposit. From both image, we can conclude that there are several layers of nanoparticles observed to have stacked on top of one another with diameters and lengths that varies, but are indeed of the nanoscale. Thus, the SEM is indeed a good way to probe into the surface morphology as well as composition of a sample. However, there are many drawbacks to this way of probing, such as requiring the sample to be conductive, and also localized damaging of the sample. But overall it provides good resolution and insight to the surface of things which we could not see, even with a normal microscope. There are also other types of SEM such as SEM fitted with an EDX detector to provide compositional analysis of the sample, or cryo-SEM to scan samples at their frozen states, or even an SEM fitted with an electron beam for lithography to provide a way for high-resolution patterning. These various SEM provides the user different functions and capabilities but, in general, still helps the operator to take a peek into the amazing world of the nano. With that, we conclude our presentation. We hope you have enjoyed it. Thank you.